Have you ever stopped and wondered what the intelligence in artificial intelligence really is? Well, today we're going to pull back the curtain and look at the hidden engine that makes it all run. And you might be surprised to find out it's a powerful mathematical language that, literally teaches machines how to think.
I mean, that's the big question, isn't it? How do you get from just lines of code to an algorithm that can actually recognize your face, or translate a language on the fly, or even create music? Where does that little spark of intelligence even come from?
The answer, and this might surprise you, isn't just about throwing more computing power at the problem or having bigger and bigger data sets. Nope. At its very core, for a machine to learn anything, it first has to be taught a very specific and incredibly powerful language.
And that language is linear algebra. Now, I know what you're thinking. Ugh, dusty old math class, right? But here's the thing our source material makes crystal clear. This is the absolute cornerstone of modern AI. It's the framework that lets machines see, understand, and interact with the world. So let's start with the basics.
Okay, so first things first. Before an AI can do any kind of analysis, it needs a way to see the world. But it doesn't have eyes or ears like we do. It needs to translate our messy, complicated reality into its own native language.
And this, right here, is the first, most critical step, translation. Everything, and I mean everything, from the pixels in a picture to the words I'm saying right now, gets converted into structured lists of numbers. Because once data is just a bunch of numbers, a machine can organize it, play with it, and eventually really understand it.
The most fundamental building block for all of this is something called a vector. It's really just a single column of numbers. And I gotta say, I love the analogy on this slide, a data recipe. Think about a vector that describes a house. It would have a number for the square footage, a number for how many bedrooms, another for the price. You get it. It's one complete recipe for one single thing.
So if a vector is one recipe, then a matrix is the whole cookbook. As our source points out, a matrix is just a grid of numbers, where each row could be a single vector or one of our data points. This is how AI organizes a massive data set. It's like a giant spreadsheet with thousands of those house recipes, all tucked away in one neat place.
All right, so we've got our data all nice and organized into vectors and matrices. Those are our building blocks. But now we need the tools to actually do something with them, right? We need to be able to shape this data, to combine it, and to pull out the really interesting insights.
And this is where the action really happens. Things like matrix multiplication, they aren't just abstract math problems from a textbook. In the world of AI, they are the verbs. They are the actual actions that algorithms use to process information, to transform data, and at the end of the day, to learn patterns.
Now, let's talk about one of the coolest tools in the toolbox, the eigenvector. Don't worry about the heavy math behind it. What's so fascinating is what it does. In a giant, messy sea of data, an eigenvector is like a compass. It points you in the direction of the most important information. It helps the AI focus on the real signal and tune out all the noise, which, as you can imagine, is absolutely critical for making sense of complex data.
So, we have our building blocks, the vectors and matrices, and we've got our tools to shape them. Now let's put it all together and see how these pieces build something we'd actually recognize as AI, like a neural network.
You know, you look at a deep learning model and it seems incredibly complex. And it is, but it's actually built from a very, very simple step that just gets repeated over and over. Each layer in a neural network just takes in some data, transforms it with a straightforward linear algebra equation, and then passes it on to the next layer. And this slide breaks it down perfectly, straight from the source paper. An input vector, let's call it X, comes in. It gets multiplied by a weights matrix, W, and that matrix is what holds all the learned patterns. Then a bias vector, B, gets added to just kind of fine-tune the result. And what pops out the other side is the output, Y, which then becomes the input for the very next layer. It's like a mathematical assembly line running over and over again. Okay, but what happens when your data cookbook has millions of recipes and each recipe has thousands of ingredients? Things get overwhelmingly complicated, fast. And this is where linear algebra is a total lifesaver, giving us these powerful techniques to cut through all that complexity. Our source flags two really important methods for this. First up is principal component analysis, or PCA. Hey, remember those eigenvectors we talked about? PCA uses them to basically create a greatest hits album of your data's most important features, so you can focus on just what matters. The second one is singular value decomposition, or SVD. You can think of that like taking a really complex machine and breaking it down into 3 simpler, more understandable parts. Both of these are absolutely essential for making AI efficient. And the list of applications just keeps going. Take something like classification, figuring out if an email is spam or not. There's an algorithm called a support vector machine, and its whole job is to find the perfect dividing line between 2 groups of data. And how does it find that perfect line? Well, it solves an optimization problem using yet another tool from the linear algebra kit, quadratic programming.
So, it's pretty clear that linear algebra is the bedrock of the AI we have today. But that relationship is always changing, always evolving. So let's take a quick look at where all the research is headed next.
Yeah, as the source paper points out, this story is far from over, and the future looks pretty wild. Researchers are looking into quantum linear algebra. I mean, can you imagine the speed-ups? They're also creating new ways to optimize even bigger models, and even using these math tools to make AI fairer by finding and reducing bias. The connection between these fields is only getting stronger.
All of this leaves us with one final thought to chew on. We often hear that math is the language of the universe. But as we've seen today, when it comes to creating artificial intelligence, it really seems like the specific dialect you need to speak is linear algebra. It's the code that translates our world into a form that machines can finally understand, process, and learn from.